Here's our question. We are driving a car uphill. We abruptly stop, slam on the brakes and skid 30 meters for 30 meters. And the claim is that we're speeding. Can we prove that we weren't? Well, let's find out. So what's the situation? We're driving uphill. At an angle of theta, which is 10 degrees. And we start off at some speed v and skid a distance l to a stop. Now, how do we solve a problem like this? Well, you could do it by forces. You could work out the backward component of the force, the acceleration, and then use s equals ut plus half at squared to see how much it slows down. But notice, what are we after? We're after the velocity. What we know is the length, and we can work out the force. A problem where you know two of energy, length, and force, and want to work out the third, can be done by work. So this is actually a prime example of a problem that can be done by work, rather easier than it can be done by force. We do need to work out the force. So let's draw a free body diagram. There's the car. We have mg here. We have a friction force there called F, and we have a normal force here called N. And we have an angle. What's this angle in there? This angle here is 90 minus theta, so that one must be theta in there. What is the friction force? It's moving. And when something is moving, the friction force is the coefficient of dynamic friction. I'll just call it mu from now onwards, times the normal force. What's the normal force? Well, the object is neither flying into the air nor sinking into the ground, so the normal force up here must equal the component of the weight down into the thing, so we know that the normal force equals mg cos theta. So substituting that in, we find that the friction force equals mu mg cos theta. So what's the energy equation? Initial energy is half mv squared. Then you add the work. In this case, the friction force is in one direction, the displacement is in the other direction, so the force times displacement is going to be negative. So the work is force, which is mu mg cos theta, times the displacement L, so it's L mu mg cos theta. So that's the initial energy, minus the work, equals the final energy, which is mg times the height. So it's h here, and h equals L sine theta. So that's equal to mg L sine theta. So here's our equation. So we've done the starting energy, which in this case was kinetic because you're moving. Take away the work done by friction, equals the final energy. It's stationary, so there's no kinetic energy at the end, but you've moved up, so there's potential energy. This is just energy balance, including work. So what can we do with this? Well, we can cancel the masses. So that's in everything here. What we want to find out is V. So we rearrange it so that V is all by itself on the left, and you end up with V equals root 2g L mu cos theta plus sine theta. Now, is this plausible? We can check dimensions. Mu cos sine 2 have no units, so we've got g, which is meters over seconds squared, L, which is meters. So you've got meters squared over seconds squared, take the square root, it's meters per second, so that's all good. How about plausibility? Well, if you skidded further, you were probably going faster. Makes sense. If gravity was stronger, then you have to have been going faster to have skidded so far, so that makes sense. If theta equals 0, so it's flat, then this is the only term, so how far I go depends, the velocity depends purely on the coefficient of friction, which makes sense. A bigger coefficient of friction means you'd need to have been going further to get the same distance. If theta was 90 degrees, you're going straight up, then this is 0, and that becomes important, so the coefficient of friction no longer matters, which also makes sense. If you're going straight up, it's just a projectile motion equation with no friction. So it all works out plausibly, and we can plug in numbers, and we find that it equals 21.2 meters per second, which is 76 kilometers per hour. To convert from meters per second to kilometers per hour, you have to convert from meters to kilometers, dividing by 1,000, and convert from seconds to hours, which is multiplying by 60 times 60, which adds up as multiplying by 3.6. So, you were speeding. Tough luck. Is this plausible? Yes, it looks a plausible speed. If it was 700 kilometers per hour or 7 kilometers per hour, it would be silly, but 76 looks at least vaguely plausible. So, I'm afraid you won't get out of your speeding rap, but we do have a correct answer here.